Hello, I'm Erik Larson from Altair, and I'm here to talk to you about two very important topics in the world of engineering: topological optimization and additive manufacturing. Whether we're talking about a family car or a race car, a commercial jet, or the next rocket to the moon, weight plays a vital role in engineering. In most every possible design field, products and systems benefit from weight savings. Pounds taken off of a car mean more miles per gallon, or volt. A few ounces can be the difference between taking home the checkered flag or watching the celebration from the pits. Weight off an aircraft means more paying customers or cargo, and a single gram taken out of a spacecraft means a cost savings of $1,000 or more. Even in everyday consumer products, an optimized design uses less material and thus is more environmentally friendly and can even cost less to build. Altair introduced topological optimization with its OptiStruct solver in 1994 and won Industry Week's coveted Technology of the Year award. In the 28 years since, Altair's optimization tools have been the gold standard in lightweighting that have been copied but never equaled. The interesting thing about optimization is that it was a technology held back by the manufacturing techniques of the age. Design restrictions placed by manufacturing requirements meant the optimized designs were excellent and saved countless pounds of weight. But the true power of topological optimization was quietly waiting to be released. Fast forward to the early 2000s, and 3D printing, additive manufacturing, is seeing its heyday. From the early days of FDM Yoda heads and embedded gear systems coming out of desktop 3D printers, to modern-day titanium SLS printers, additive manufacturing has finally unleashed the true power of topological optimization. Finally, the organic and revolutionary designs coming out of Altair's optimization codes could be realized in metal 3D prints that could never have come out of traditional manufacturing technology. As 3D printers became larger, faster, and more technologically advanced, you will be able to see more and more optimized parts in everyday products, on the roads, in the skies, on the trails, ocean, deserts, and even in your homes. So now that we have an understanding of what optimization is, and why it's critical to the engineering process, why don't we take a look at how we go about doing innovation? Now this is just going to be a demonstration. We're not getting into the specifics of the utilization of the software. I do have many videos on that, provide information about where to find them if you want to do this for yourself. But let's just go through the process of optimization and better understand what a software does to achieve optimization. So this is Altair's Inspire software. Inspire was created as a tool to allow easier access to topological optimization. Optimization analysis had always been kind of relegated to people who had a deep understanding, background, knowledge, training in doing analysis and optimization. And we wanted, at Altair, we wanted to kind of bring that to more people. And to do that, we needed to make it easier to do. And that's where Inspire comes in. Inspire is entirely geometry driven. In fact, let me come here and open up a model that we're going to do. So this is going to be the part that we're going to optimize. And you see it's just coming in as geometry, and we can support any of the geometries that are out there, all the popular CAD systems, the intermediate formats like Step, Parasolid. And we're going to take this part and we're going to run it through a quick analysis just to see that this is a part that could be optimized, a better design through optimization. And then we're going to walk through the steps to do an optimization. So this is an aircraft door hinge bracket. This is a 380 part. And its job is to attach two of these attached to the frame of the aircraft, two of them attached to the door of the aircraft. And then attached to this little cylinder here is the actual aircraft door hinge, which allows the door to open and kind of lean out and lay against the side of the aircraft. So needless to say, it's an important part. And as with anything aerospace, weight is everything. And we want to make sure our parts are as light as possible. But also important to aviation is, of course, reliability. So we want to make sure the part is survivable. It will achieve whatever goals we're looking to set for it. So if I want to take this part and I want to see where we are right now, what the status of the design of this part is, I can very easily do that in Inspire. The first thing I'm going to do is assign a material to it. We have an entire list of materials here. I'm going to select one. We can add materials as well if we so desire. But I'm just going to select aluminum 7075 T6, a very popular aviation grade of aluminum. And we can take a look now and see what the mass of our part is. And we're looking at about 1.5 kilograms. If we wanted to see that in pounds, we could just very easily change our unit scheme, and now we can see it's about 3 1/3 pounds. We'll stick in metric units. But transferring or changing units within Inspire is very easy. It's just coming down here to this little selection down here. Units actually can be one of the more difficult parts of doing any analysis or optimization, making sure you have consistent units, and Inspire makes it easy through these easily accessible unit schemes down here. And the nice thing about it is I can switch those units at any point in time, and any of the materials, the loads, size of the part, all of that will just adjust to the new unit scheme. Nothing will physically change on it. Anything that is, anything that, darn it, sorry, anything that is a specific size or a specific load, it will now just be represented in the new units. It'll be the exact same style or the same size of part. So I'm going to come here, and the first thing that we need to do is hold this in place, and I'm going to do that through the use of what we call constraints or supports. And I'm going to select these little holes here, represent this as if it were bolted to the aircraft structure. So that's what you're seeing here, these little constraints. And what they do from an analysis standpoint is they hold the part in place. Looks like I additionally ended up with one somewhere else. Need to find out where that went. There, this one right here. This is not right. So let me just get rid of this one. There we go. Get rid of that. Okay, so we have our 6 bolts in place. It's important to the analysis because the part does have to be held in place. If we put a force on something that's not held in place, it would just kind of fly off. So I've got those bolted in place, and now I'm going to add a force to this. And I can add a force to a surface, to a point, to a line, anything that I want to apply it to. I'm going to put it at the center of the hole here, and this is going to represent, where did it go? It did not go in the center of the hole, so let me get rid of that, and let's select this again. There we go. Now we've got our force there. So it's this little force marked with an F, and I can orient that in any direction I want. I can even come here and rotate it, move it in any direction that I want, but I just want this to be pointing in the negative Y direction. And we'll give it a value here. I'll say 2,000 newtons. And you can see it tells me in advance what the unit of force I want that to be in. So I make sure I put it in terms of newtons, and now I have that force here. What I want to do, though, is I do want to analyze this with multiple loading scenarios. So this is going to represent a situation where the door is open and 2,000 newtons of force are going to be pulling on that hole. Put another force on this, put it on that same hole, and I'm going to put this one in the positive Z direction. Now, say for instance, I knew this to be 500 pounds of force. I didn't know what it was in newtons, and I could probably relatively easily convert that. But a nice thing about Inspire and the unit systems that we use here, I can type in 500. If I were to click enter now, it would just be 500 newtons. But if I type in LBF for pounds force, knowing that it wants it in newtons, it automatically does the conversion for me. So a nifty little trick that we can use there. So now I have these two forces. As they're set up right now, they would act simultaneously, which would of course be a bad situation. I can't have the door open and closed at the same time. These two forces will never act together. So the way that we handle that is through a process called load cases. Load cases are different studies that we want to do on the part. They'll be done in the same geometry. They'll be done in the same analysis, but the forces won't apply at the same time. If I add another load case here, I can then just kind of go through and select the supports that I want. So what constraints do I want to use, and then select the force that I want, and I'll deselect that there. And now I'm going to get two entirely separate results out of the same analysis run, which makes things very easy. It doesn't mean I have to create, or it means I don't have to create multiple models, run it multiple times. It'll all happen at the same time. I can continue to add load cases as I want. So say for instance I want to simulate a situation where these two bolts have failed, so I just won't select them, and then I can pick a force, and I can continue adding different loading scenarios. Even with different types of loads, you see we have a temperature load that we could add, but I'm not going to do that in this one. But we can continue to add as many different load cases as we want. And now that's done. It's ready to analyze. I've got my two loads on there in two different load cases, so we'll get two different results. I've got my constraints in there, so now all I have to do is come over here and actually analyze the part. I click the little play button. It opens up my analysis window. I can name this whatever I want it to be. So we'll call it, bracket study. And if another nice thing about Inspire is every time I do an analysis, it's saved within the model. So I could say call this bracket study 1. And if I wanted to study it with a few alterations to the model, I could do that and then call that one bracket study 2, and I'd be able to compare the results between the two of them. So a nifty little way of studying different type scenarios. Another thing that I could do is I could get the normal modes off of this. So if the modal frequency of the part were important to me, all I have to do is click that, and it will automatically go through and add all the necessary information to do a modal analysis as well. And then it's just a matter of clicking run. Now what will happen, and some of the true power behind Inspire, is it is utilizing our enterprise level softwares to do the meshing in the background. You see I didn't have to do any form of meshing myself. That'll all be handled automatically for me, and then it's going to use our OptiStruct solver to run the analysis on this. So while it was incredibly easy to set up, I can rely on the results because it's using a tried and true analysis tool that we've been developing for now, well, close to 30 years. So we know that the results, even though it was deceptively easy to do, we know the results are going to be correct. And from here, I can now just take a look at the results. I can come up here, I can animate it so I can see how it deforms. Now the animation is actually scaled up. Let me slow that down a little bit. There we go. So that a little bit slower. The animation is automatically scaled up. You can see the actual deformation of this part is incredibly small. We're at 5/100ths of a millimeter there, so very small. So it's scaling it up just so I can see how it behaves. If I were to go and change this, which would be very easy to do, to 1-to-1 scale, we wouldn't see any deformation at all. You'd have to really zoom in to see it moving. So that's why we automatically scale it up. And I can take a look at the two different load cases, or three different load cases. So this is the other one and how it deforms there. And then the one where we simulated the two bolts failing. So we get that, and obviously substantially more deformation there. And finally, I can come here and take a look at the normal mode. So it's telling me that the first frequency, the first natural frequency of this is 4,575 hertz, and this is the way that it will vibrate. And I can take a look at the first 10 of those frequencies. They get progressively higher and higher, and progressively more and more complex. But what I really want to look at is the stress on this part. So I can go back to my initial load case, and I can come down and take a look at my von Mises stress. And now I'm seeing von Mises stress. The blue is low stress, or stress that's below the yield point of the material. The white is going to be stress that's right at my yield point, and anything in red would be stress above the yield point. So you can see it's very, very low stress on this part, and in fact in both load cases. The majority of the stress we're seeing is actually down here right along the edge here. This is artificially high stress. It's an artifact of finite element analysis. Anywhere you've got something rigidly constrained, it's going to artificially raise the stress. And the fact that it's just in a very small area tells me that it's an artificial stress. In fact, I can even take a look at the mesh that it did apply to this, and we can see that stress isn't even coming out of the first element, which tells me that it's just an artificially high artifact of the mathematical process of solving this. And then what I'll do is I'll actually change this to factor of safety. So this is the true telling of how well built or how well designed this part is, this factor of safety. And I can use this, let me come back actually to von Mises stress. I can use these little arrows here to filter out things that are above or below a certain value, so we can see where the highest stresses are. And if I come back to my factor of safety, you can see that I'm above a 6 times factor of safety on the entire part in both loading cases. So this part was designed well, but actually this part was over-designed. There is no scenario in which we need a 6 times factor of safety on a part like this. Where you think, well, hey, 6 times factor of safety, that's fantastic. It means this part's never going to break, which is really nice. But if you think about it, if the entire aircraft, every single part were made with a 6 or more times factor of safety, you'd be lucky if that plane would ever lift off the ground. It would just be way, way too much. We typically design to a 1.5, 2 times factor of safety, somewhere around there. So while this part was designed well, and it looks like they did put some features in here to try to lightweight it, it's way, way over-designed. And that now relates back to our discussion of topological optimization. The idea is to make the lightest part possible, the least material usage part possible, to achieve the goal that we're looking to achieve. Excuse me. And that's where we want to go with optimization. You can see they attempted it with this, as I pointed out, these little pockets that were put in here. The fact that this has been kind of carved off at angles. They've reduced material usage, but they just kind of did it in a, I won't say haphazard manner, but they did it in a manner that's kind of common. Is you look for areas where there's not a lot of stress and you just take some material out of there. What we really want to do is utilize simulation in the design process. Allow an algorithm, allow the science of the finite element analysis to help us better understand true material necessity. What material is truly necessary, what material is not necessary. And it's just something that we can't do on our own. Is something that we need analysis to help us with if we truly want to achieve an optimized design. So let us leave the results here. And now I want to prepare this for an optimization. And to do that, I actually do need to make some geometric changes to this part. So in the kind of the prelude to this, we discussed that optimization is like carving a sculpture. It's the removal of unnecessary material. But just like an artist would never carve a sculpture out of a sculpture that's already been carved, we don't want to optimize out of a part that has already been somewhat optimized, somewhat revised here. An artist is going to take a nice big block of material, marble, wood, whatever, and they're going to carve from it. They're going to just pick a block of material that's large enough, but just large enough to fit the statue that they want. And that's what we really want to do with this geometry here. We want to have a chunk of geometry that doesn't have all these little fine-tuned features on it, that the algorithm can then go and determine what of that material is necessary. And we call that a design space. And so what I'm going to do, and this could be done in a CAD package, but it's pretty easy to do here in Inspire. I'm going to come in here and I'm going to simplify this. The first thing I'm going to do is fill up some holes. If I double click on this, it's going to identify that pocket. If I click it again, that pocket goes away. And that's why, even though this could be done in a CAD package, in a lot of cases it's actually easier to do in Inspire because we have tools designed specifically for this. So I'll fill those in right there. Now, to deal with these angles here, I come to this tool here called push-pull. Push-pull is a nifty tool. I pick a surface and I can literally push or pull it. And if I keep pulling it all the way to the point where those two surfaces meet, I get that nice 90-degree angle there. I can pick another surface here and I can drag that out, and I can drag this out as well. And now we're kind of seeing where we want to be. We want a block of material, no fillets, no little fine tuning areas on it at all. Just a nice big block of material that fills up the volume that we can have, or that we can utilize in the design, but doesn't go beyond it. You see, I didn't do anything to fill in kind of this area in here that we can't have material there. It is going to remain like that because this needs some clearance for the hinge to clear it. So anywhere I don't put material, I won't get material. Just like if I'm carving a statue, I can't end up with a statue that's larger than the block of marble that I began with. Optimization is the same way. It's 100% subtractive. Interesting, because ultimately we'll get into the discussion of additive, but it is 100% subtractive. So the maximum amount of material you can have is represented by the geometry, and then it will remove from there. So we just leave off the chunks that we don't need. Like these little pockets. I need these little pockets here because I need to be able to reach in with a wrench and grab the bolt. I need these rectangular areas removed so the hinge can fit around that, but the rest of this big block is subject to removal. And kind of along those lines, there's a large chunk of material that we can remove from, but there are aspects of the design that are critical. For instance, I need this to be a perfect cylinder of this size in that location so that the hinge can bolt to it. I can't have the software removing material from that. So what we do is we partition that off. We create what we call non-design spaces. It identifies things like that. So I pick that hole. I tell it how thick I want that region to be. 5 millimeters will work fine. And now this is an entirely separate chunk of geometry. So when I right-click on my main part here and I say this is design space, now the big red area will be that material that can be sacrificed, that the solver will determine what is necessary and what's not and get rid of what's not, but it won't touch this. So I'm always guaranteed of having that nice cylinder there for the attachment. The same thing with the bolt holes here, so I could come down and select this. Now I don't want it to protect that pocket. The fact that that pocket is there is all I care about, to make sure I don't have material there, but I don't need it to remain this perfect little cube. So what I can do is I can take off those two surfaces there, and then when I pick these two cylinders, I'll get that, and then I would continue on and do that around the part. But in the interest of time, it's a little repetitive. Let me just kind of cheat here, and I'm going to come up here and grab this part let's get rid of these right now because I don't want to discuss putting those on there. So now you see, excuse me, we've got that cylinder maintained with our forces in it. We have our bolt holes maintained. And now this is an ideal part for optimization. But those pieces that the things that I got rid of initially, I got rid of them because I wanted to talk to you about what they represent, and that's back here in the structure, and shape control. So when we were in the preliminary portion of this, we talked about different types of manufacturing. This is where we would incorporate that. So if I need this to be a drawn part or a split drawn part, which is either a casting or a stamping, with this little image that appears, we can kind of see what the difference would be. If it's a single drawn part, it's going to guarantee that all of the material goes in the direction of the draw. It makes sure I don't have any undercut areas or any holes, so that if I'm casting or stamping this, I could remove it from the cast, or I could remove it from the stamping. Split draw is similar to that, but it allows for a draw in two different directions, which means I can have things like these little legs sticking out. Extrusion, we talked briefly about that. Extrusion is where I've got a constant profile going through the part. So these are the main, the three main manufacturing techniques that we can incorporate our optimization to try to make sure that the part maintains a structure that allows it to be manufactured through a traditional sense. But this is where technology has kind of caught up with manufacturing. And optimization. Optimization has been around. Like I said, we introduced it 30 years ago, or almost 30 years ago. But at the time, it was all standard manufacturing processes. We didn't have 3D printing or additive manufacturing. Additive manufacturing is kind of what optimization has been waiting for. Optimization comes up with incredible designs, but left to its own devices without incorporating these manufacturing processes, they just plain out couldn't be made. But additive has changed the game, and that's why additive is kind of the manufacturing process of the future. Additive allows us to have the optimization code do its thing without the restrictions of manufacturing. Because with additive, we can make just about anything. You've seen 3D printed parts of something encapsulated in something else, or entire designs that have an entire internal structure with them. That's the way that manufacturing is going. For instance, General Electric Aviation Division, they make jet engines. They're embracing additive manufacturing because now they can incorporate things like tubing or cylinders inside the part that they previously couldn't do, and they'd have to actually just run tubing. But now we can incorporate that all into the part. As long as it's something that we can 3D print or use additive manufacturing. So it's almost as if topology optimization was ahead of its time, and it was waiting for something like additive manufacturing to come along to truly take advantage of these amazing optimized shapes. And you'll see that when we finish this optimization. One restriction I am going to put on it, though, is what we call a symmetry restriction. So I'm going to put our constraint. I'm going to select that body there, and now it's going to give me three main planes of symmetry. I'm going to turn these off. What I want the part to do is be symmetrical about the central plane, and what that means is I'm going to have a universal part. It can be put on either side of the aircraft or in either orientation on the frame or on the door. And it allows me to get a part that's universal. If I did not include this, you can see we're just looking at a force in this direction. It would optimize it, taking care to place material to take into account that force, which means that we'd end up with a part that's not symmetric. And if I were to flip this part over and the force would be running in the opposite direction, this part would not be properly optimized for that direction. By putting a plane of symmetry in there, it allows me to, whatever it does to optimize for this load on this side, even though it normally wouldn't want to do it on that side, it's going to be forced to make a symmetric universal part. So we can take advantage of some of the constraints, the controls, to guarantee that we have a part that is universal or can be used on either side of the aircraft in any orientation. And that's it. It's ready to be optimized. This big red area, anything that you're seeing in red, can be carved away if that material is not necessary. Anything that's in gray will be maintained. So we're going to have our nice cylinder there and our bolt holes. Now we just go to the optimization. If I come here to optimization, we've got, when we do an optimization, we have to have an objective. What is our goal? And yes, I realize that our goal is to lightweight the part. But in the process of doing that, there are some other considerations we might want to make. For instance, this maximize stiffness, the first and most commonly used optimization technique. What maximize stiffness does is it optimizes the part to be as stiff as possible. But left to its own devices, if we didn't tell it otherwise, well, the part you're looking at there that is utilizing this material is as stiff as possible. So, but we want it to be lighter weight. So what we do is we set a mass target on it, a mass target of 30%. What that means is this big red area, I'm telling the software, you only get 30% of the mass of this big red area here. And whatever 30% you use has to be oriented in such a way that it maximizes the stiffness of the part, makes it as stiff as possible. 30% is the default. It's just something after decades of doing optimization we've determined is a good starting point, but it doesn't necessarily mean that's going to be the ending point. If it comes out still too over-designed, we could reduce that volume. Or if it ends up too weak, we can increase that volume. But it's a good starting point. We can also incorporate frequency constraints to maximize the frequencies or set a minimum frequency if that's something that's important to us. And quite often it is. In this particular instance, I'm not going to utilize that. But it can be incorporated in there. What we're going to actually use is this minimize mass option here. Minimize mass now, the goal for the solver is to get rid of as much of this red material as possible. So I'm not giving it a specific amount to get rid of. I'm saying get rid of as much as you can. And of course, left to its own devices, with that as the only requirement, it would just make this entire red area go away and say, hey, there's the minimum mass you can possibly have. So I have to set a restriction, and now this is where I can incorporate a stress constraint. So as material gets removed, stress is going to go up. The less material you have, the less of the cross-section, the more stress you're going to have. So what I do is I set a stress safety factor, and this is where we were talking about safety factors. I'm going to say a 1.5 times safety factor. What this means now is get rid of as much mass as you can. But as stress begins to build, it always has to remain underneath this safety factor here. It has to, if it starts to see that the stress is creeping up and achieving that, reaching that safety factor, what the safety factor does is it takes the yield or the failure point of the material, it divides it by 1.5 and sets a limit on the stress that way. And that's what we're actually going to run. And so now I will just run it. And it will go through and run. Now this is going to take probably about 5-7 minutes to do. So what we're going to do is just pause here, and we'll bring you back when the analysis is complete. So just like that, through the magic of editing, the analysis is now complete. You can see we have a topology choice over here, and if I select that now, we can see what the solver has determined as the optimum placement of material. And you can see that this is not a part that we would traditionally be able to engineer on our own. This is way outside of what we can kind of imagine as engineers. And it is a optimal usage of material. What I can also do with this is if I feel it's a little bit under-designed, I can add a little bit more material to it, or I can subtract material away from it, and we can end up with a truly optimized part. And you can see this is not something that I could traditionally cast. There's holes running through it in multiple directions. I couldn't stamp this. This is why additive is what optimization has been waiting for, because this would be an incredibly simple part to create through an additive process. Little bit, you know, I'd have to have some ports here or something like that, but that's kind of the nature of the business when we're talking about additive. But this is the best, most optimized version of this design that's possible. One thing you may have noticed right off the bat is it has abandoned these two bolt holes here. That's not uncommon, especially when doing a stress-related optimization. In this case, what it has determined is these two bolt holes don't contribute to anything connecting to them, doesn't contribute to reducing the stress on the part. And we can kind of see if I'm pulling up here, it's going to be between these and these. These middle ones really wouldn't be doing anything to stress, and if I'm going sideways, it's going to be these and these, or sorry, these and these that are going to be reducing the stress. These really don't contribute to it. But maybe this is an aviation part. Maybe the FAA requires that we have 6 bolt holes for every door hinge bracket. I could rerun it, add a little bit of a force here that would force a load path through and it would connect it. Or optimization in this case, this isn't telling you this is exactly what the part has to look like. This is telling you this is how the material should be distributed to guarantee that that the least amount of material is utilized. But I could engineer in myself some sort of connection. Maybe I could connect it around this way, or bring down kind of like a V shape here, or another arm coming down. I can take this back to my CAD, and that's really as simple as just coming back to here, clicking Fit Polymers. Before I do that, though, I do want to double check this. So I can very easily just click Analyze. It's going to take my design as I've got it right here. It's going to apply those forces and those constraints to it, and it will allow me to make sure that with this part, as it has been optimized, make sure it achieves the goals that that I've asked it to. And this should be a relatively quick analysis here, and it will act as a double check, a final check to make sure that the optimization did what I wanted it to. So as quickly as that, I can come here. You can see we have increased the displacement. That's not surprising. The part does not have as much material, but it's still an incredibly small displacement. But most importantly, if I come here to my factor of safety, you can see the factor of safety has gone down. I have regions that are not 6, but if I drag this all the way down, I've actually got a 2 times factor of safety on this, and if I come to my lateral loading, I've got just under a 2 times, or right around 1.5. So I have achieved my goals. This part will meet the requirements that I have set forth on it, just meet them, which is fine. The reason I set a factor of safety is because that is the minimum that I want. So now I have the minimum amount of material necessary to achieve the factor of safety that I'm looking for. And you can see through this, I have actually reduced my part from, was it 1.5 kilograms down to 0.35 kilograms. It's a third, less than a third of the mass that it was before. And what's that mean to me? Well, it means, first of all, if 4 of these are going on every door, that's 1.2 kilograms or 1.1 kilograms per part. So that's 4 kilograms, 4.5 kilograms of weight reduced for every single door that's on the A380. And I don't recall offhand how many there are, but there's probably a good 10 doors on that thing. So that's 40 kilograms, 45 kilograms of mass that's been reduced. I've reduced my material utilization in general, so the part is it's greener. It's using less material. I have less waste, especially if I'm looking at it in an additive process. So overall, the part is a substantially better design in every aspect, and that's what optimization does for us. That's the true power of optimization. Create an ideally designed part, something that I typically wouldn't be able to come up with on my own, and allow simulation to drive the optimization and the design of the part. So what do I do with it now? I can double click on it, click this little fit polyNURBS button. What that's going to do is it's going to fit geometry, nice smooth geometry to this shape. Should only take about a minute or so to do. And once I have that geometry, I can save that out to an IGES, a step, or a parasolid file. If I just wanted to go straight from here, once I have that geometry, I could actually even save it as an STL file. I could bring it into whatever my favorite slicer is, and I could take this part and immediately go to 3D printing. So you see we have a very nicely designed part here. Even if I did nothing to it, this is a great part that could be very easily 3D printed. More than likely what I'm going to do is I'm going to grab this geometry, I'm going to bring it into my CAD package and do a little bit of fine-tuning work on it, and then I'll have a fantastically designed part that is much lighter than it originally was. It's much better material utilization, and it is still a 100% safe part because it meets the requirements that I had. That's what topological optimization does for us. So that's kind of an overview of topological optimization. Again, this wasn't an attempt to train you in the software. That would take a little bit longer. Altair has a number of videos that I've done on our YouTube channel. Altair University on YouTube. Look for the Inspire instructional video series if you want to actually learn how to use the part. If you want to download this software for yourself, we have a student edition that can be downloaded from altairuniversity.com. I'll pop up a little display here as how to get that. But you'll get a fully licensed version of this software that you can use for yourself, and you can try out some optimization for yourself. It's a great tool, and I can't stress enough that optimization has been waiting for 30 years for additive manufacturing to come along and truly take advantage of an optimized design without the restrictions of traditional manufacturing processes. But they aren't going away anytime soon. Heavily used in aviation because they can do a lot of 3D printing. In automotive, they're still doing optimization, but they're having to restrict themselves to the traditional manufacturing processes. Additive manufacturing isn't there yet. It's a great tool, but it just isn't fast enough. You know, if you took the combined production levels of Airbus, Boeing, Bombardier, all of the different Embraer, all the different aircraft manufacturers, their yearly production is probably less than a single day production of any one automotive company. So additive still has a ways to go to be adopted in every industry. It will get there. We are, believe it or not, still in the infancy of additive manufacturing. But you're going to see a lot more designs that look like this and moving away from your traditionally orthogonally designed parts. Additive manufacturing and topology optimization are the future of engineering and design. Thank you very much.